Hello, my name is Mike Zorn, and I'm here with my colleague Justin. And today we're going to talk to you about how you can use feature flags to avoid downtime when running cloud migrations. And before we talk about exactly how to do that, let's start by thinking about a really complicated migration. The San Francisco-Oakland Bay Bridge. This is a bridge that spans San Francisco Bay. It was originally built in the 30s, and when it was built, it was something that took about 10% of 1 year of domestic steel to build. So it was a pretty massive piece of infrastructure, something that you might think would last forever, but it was damaged in an earthquake in 1989, and the eastern span of it, which is shown in this picture, had to be replaced. And it took 11 years to build a new bridge and replace the old span. And this is something that hundreds of thousands of cars are going to go across every day. So one thing you might wonder is, when they built this new span, how did they get the cars from the old span to the new span? You can't just tell everybody like, hey, like starting now, go on the new bridge. The lanes aren't hooked up. So what they ended up having to do was close the bridge for 5 days while they reconfigured the lane so that cars could only go on the new span. So do you remember the last time you took critical infrastructure down for 5 days? In today's software industry, you probably don't. If your product has an SLA of 4 nines, which isn't uncommon, that means you can have 52 minutes of downtime a year. But at the same time, do you remember the last time you built a system that ran continuously for more than 50 years? Probably don't. Cloud infrastructure is something that changes pretty fast. There's new AWS instance types around every 2 years. This means that software engineers are, migrating infrastructure far more often with a lot less tolerance for unavailability than a civil engineer would be. But the good news is that there are a lot of tools and advantages we have in software that you can't use in the physical world. One of them is feature flags. And today we're going to talk about how we use feature flags for migrations. So we just went through an introduction. Next, I'm just going to briefly talk about what feature flags are. And then we're going to go through kind of two sort of case studies. One is a high throughput data processing system, and one is the core data store that powers LaunchDarkly. And Justin is going to talk about that second one. So first, what are feature flags? Feature flags are a tool that lets you deploy when you want, but decouple that deploy from your release so you can release when you're ready. So the idea is that you ship some code to production, it's behind a flag, you turn it on for your test account, test it out. If it looks good, then you turn it on. And then it also allows you to ship incomplete features and not have terrible merge conflicts and this sort of thing. And then here's what that looks like in code. Here's just a simple example in JavaScript. We have this flag, my cool flag, and when it is turned on, this logs very cool. And this is pretty simple, but as you can see, changing the value of the feature flag in our LaunchDarkly control plane lets us change the runtime behavior of our application without needing to redeploy it or restart a service, anything like this. And what's more than just changing the runtime behavior, with a tool like LaunchDarkly, you can actually change the runtime behavior with very low latency. So when you change a flag in LaunchDarkly, that value is going to propagate to your application unless it was sub-second latency. So this means that with a click of a single button, you can change the runtime behavior of your application in less than a second, which is great for rolling out new features. It might even be a little bit overkill to have that amount of, or like that small latency just to roll out a new feature. But that low latency enables some other use cases. One of them is like a kill switch, like say some features, performing poorly in production, we can turn it off immediately. You don't have to wait for a deploy or anything like this. Another use case we've explored internally is to change your monitoring fidelity. Like, say some customer has a support issue, being able to just turn on debug logs for that customer is a really good way to get to the root cause of the issue they're running into faster. And then the use case we're going to focus on today, though, is migrations. And now that we've talked a bit about feature flags, let's dive into the LaunchDarkly events API, which is the high throughput data processing system we're going to talk about for our first migration case study. So here is a picture of what event processing at LaunchDarkly looked like around 2017. You have a LaunchDarkly SDK installed in your application, and it sends some information back to LaunchDarkly about which feature flags are being evaluated and who saw them. This allows us to show you things like, what flags are in use, this kind of stuff. The way this worked was, the SDK would send it. That data would then arrive at a load balancer, which would, route the data to a bunch of application servers. And then those application servers were actually writing to numerous databases, within that application process. So there's a bit of a problem here where there's no back pressure. If any one of these databases starts slowing down, we can tolerate it for as much data that we can buffer in that application memory. But once we overflow that, the application just crashes and you lose a bunch of data and your API goes down. And that's not good. When we were just showing flag statuses, that wasn't horrible. But we needed a new architecture because we wanted to invest in some new features like experimentation, where data loss would be problematic. And we also needed to have a system that was scalable to more features. Like in this system, every time you added a database, you added a new failure mode if that database went slower. We wanted to have a system that, when you added a new feature, didn't add a new point of failure for the entire system. So we just added some kinesis to it. What we did was we put a kinesis queue in between our application server and where the data got processed and written to other databases. And we moved that data processing and writing to these downstream databases into AWS Lambda. So what this allows us to do is, we write all the data to this kinesis queue, and every time we add a new feature, there's this queue in between. So if the new database that powers the new feature slows down or stops working or something, we're still going to have that data in the queue, and we'll be able to get it out later, as opposed to having the data in our application memory where it would just go away forever. So we're kind of adding two new things here. We're adding these writes to this kinesis queue, and we're adding this Lambda function to do all of the processing outside of our application. So we decided to do this migration by having kind of two switches, where each of these kind of chunky arrows are. We have one switch to write to kinesis, and then one switch to do the processing in Lambda. And when I say switch, I mean feature flag. So we have one feature flag that governs when we write to Kinesis and one feature flag that governs when we process to Lambda, in Lambda. That allows us to kind of migrate in phases. We can first test out our code that writes to Kinesis, and then once we're happy with that, once all the data is in this queue, we can then kind of process fractions of it in Lambda. But that actually creates a little bit of a problem. So we have two feature flag evaluations going on, one in our application and one in our Lambda function, because we have these, the two feature flags we talked about. But there's a bit of a problem because these two evaluations happen at two different points in time. And when there's a gap in time, something could happen. Like example, you remove a user from the B flag, which is the one that governs where the data is processed, after it got written to the queue. So that means that any data that came in this time period is going to it will not get processed because we remove that user from having the processing happening in the Lambda function, but after it got written to the queue. So we decided not to process it in our application, but then we changed our mind and decided not to process it in the Lambda function after that. So that creates a potential for data loss, which we do not want. So the way you can work around this is you do all of your the flag evaluations when you're writing the data to the queue, and then you add some metadata to the event that's getting put in the queue that describes where the processing should happen. And by doing that, you do all the flag evaluations at one moment, and there's no gap in time for some change to slip in. And this is how you can have these two stages to your migration, but still avoid any kind of data loss around changing flags. So once we had this kind of detail worked out, we were ready to do our migration. And we had a workflow for that day-to-day looked something like this. You would turn on the new architecture for, say, 30% more traffic, and then you'd notice a graph goes up and to the right. And then you turn it off. You switch that 30% traffic back to the old way, figure out why that graph went up and to the right, and repeat. There's on that architecture diagram, it looked like, oh, okay, we're just adding a couple boxes. That shouldn't be so hard. But when you move from a handful of servers in EC2 to a Lambda function running with hundreds of concurrent execution, you have a lot more concurrency that kind of changes your workload a little bit. So we had to work through some issues around that. But it was fine because you can recall that we had these two flags. So we didn't start rolling out the data processing in Lambda until we had all the data written to the queue. It really gave us kind of some safety where we could turn on this, change this knob for how much data we're going to process in Lambda as we sorted out these issues we ran into as our workload changed. And you can kind of contrast that with how the cars got on the new bridge, right? Like they had to do a lot of upfront testing because once you have the cars on the new span, you got to shut the whole thing down for 5 days if you need to go back. Whereas here, we just flip a switch and go back. And then, but the thing with the bridge also is that the cars are going to have predictable characteristics. Like there are organizations in the U.S. government that set standards for how much cars weigh and how wide they are, this sort of thing. We have that a bit in our application, but some of the data we get from our SDKs is a little bit unpredictable. And you don't realize these things until you're in a production environment. So having the ability to kind of turn some traffic off as we ran into new things, is something that you couldn't do in the bridge. but it was a difficulty that's maybe a little bit unique to software. So we've got our traffic going through, and once we iterated through this process a few times, the migration was complete. We got all the data into the new system, and we were able to do that. When we did that, we avoided data loss by decoupling our data processing from our persistence. We were able to avoid losing data while we migrated the data processing to Lambda and kind of work through some kinks. And additionally, we're able to deliver value kind of sooner than we would have if we did a ton of upfront testing. So we kind of worked through issues as we ran into them in production, and then relied on feature flags to kind of move the traffic back as we found new issues. And all the traffic that we had, we had traffic going into the new system the whole time. So all of the customers who were going into the new system were kind of realizing some new value. Like in particular, we were migrating customers that wanted access to our newer features that had more kind of data integrity sensitivity. So we were able to get those people on the new system, even though the new system still had some kinks that we were working out as we scaled it up. And we iterated through this a bunch of times, and avoided kind of some expensive upfront testing as well. So that is how we migrated our events API from our old system to our new system with feature flags. And we got these characteristics of avoiding data loss, delivering value sooner, and iterating through things instead of a big upfront test or something like this. So now I'm going to hand it off to my colleague, Justin, and he's going to tell you about how we migrated our core data store.
Thanks, Mike. So we just heard from Mike about how we used feature flagging to safely transition some of our infrastructure to a new Lambda and Kinesis-based pipeline. I'd like to turn now to talk about another type of infrastructure migration that I think is pretty common. This has to do with migrating databases. So what are some reasons we might want to migrate databases for application? There's lots of reasons. It could be that our product has grown a lot, we have a lot more traffic, we want to move to a global infrastructure from a regional-based one. We might have some pain points with our query model or the isolation properties of our current database. We might want to invest more in resilience for our database. Plenty of reasons we might have just made a mistake in the database we chose initially. In our case at LaunchDarkly, we had a lot of success using Mongo for a number of years, but in 2020 we decided we'd like to look for databases that could withstand a regional outage without any service interruption or data loss, while at the same time giving us strong isolation and consistency guarantees. We also had a preference engineering-wise for using SQL, and we thought that would fit better with our data model, which was pretty highly structured. So we decided to go with CockroachDB. However, our particular choices aren't really the point of this talk. I'd like to talk more about general techniques for how to do such a migration. You could be going from RDS Postgres to Dynamo, from Aurora to whatever, any two databases basically. And the key constraint that we had in doing this migration work is that we don't want our users to notice. So having a maintenance window is just not acceptable. We need to be up all the time. Users always have to get correct data. We can't give back wrong answers because we made some error in our new database. And the migration must not cause any performance regression or degradation of the user experience. So what do we want? Ideally, we have this before state and then the after state where we're connected to the new database and the old database has been disconnected and we can retire it. And this is, harks back to Mike's picture of the cars on the bridge. How do we get the data in blue onto the new database safely and without interruption? If only we could snap our fingers and just have the new database in place, but of course we can't. So we need a process to get us from the before state to the after state safely. That process needs to be gradual. Small changes are a lot less risky. Those changes need to be reversible. And if we do need to reverse a change, we need to be able to do so immediately. And this is where feature flagging really comes into play. It gives us the dynamic control that's internal to our application. We can't rely on a redeploy to make these kind of changes. It just takes too long. We also need our changes to be verifiable. So does the new database give the same answers as the old one did? And we need to produce metrics and some observability into that verification. So we'll start off the migration by simply connecting our application to both databases at the same time. And the old database will be what we call the active database, and the new database will run in this idea of a shadow mode. So that means that our application is sending the same queries and operations to the new database as the old one, but the new database is completely disconnected from our user's experience. This is a little trickier than it seems. We don't want to introduce performance problems, as I mentioned earlier, if something goes wrong with the new database. So it needs to be isolated pretty well. We'll start the new database out empty. And as we start sending writes to it, it may begin to fill up, depending on your data model. So now what we'll do is we'll just be in this sort of dual reading state for a while as we iterate until we're happy. Now, I mentioned a bit about how to fill up the new database. And this really is a your mileage may vary kind of issue, but we need some sort of process that will sync data from our old database into our new one. This also probably depends on how large your data sets are and what tooling you have available. In our case, we were able to get by with pretty simple, essentially like sync style scripts that we could just run queries on to bring some slice of data over into the new database. And we need this because even though we're actively writing to the new database, it doesn't have all the data that was there before we started this migration. So all that data that's been in there somehow has to get over. So once we've got that syncing working pretty well, we can engage in this loop that's shown here where we verify that both the old and new are giving us the same answer. And if we find errors or deltas between the two, we do some fixes. We also are observing the performance of the new database. And as needed, we're optimizing that or changing the queries or adding indexes, whatever we need to do to get the performance at the same level it has been. And we just sort of loop on this, on these fixes until we're happy with how things are working in the new data store. And of course, if anything goes wrong, because we feature flagged the application, we can disconnect the shadow database just by flipping a switch and just go back to our status quo, which is using the old database. And then once we're happy, we make the switch and we connect to the new database and we drop our connection to the old one. This means that user experience is now connected to our new database. And so they'll be getting answers out of there instead of out of the old database. So how do you actually make this work in your code? Let's dig a little deeper and see what we have to do in our application for this to happen. LaunchDarkly is a Golang shop, so I'll go through some Golang examples, but I think these principles could apply for other languages or ecosystems. And the point of these examples isn't really to get into the code so much as to understand the complexity around doing this kind of thing. So let's say we've designed our application so that our data access is hidden behind an interface. So let's say we have an idea of an account and an account repository with a find method on it that looks up accounts in the database. If you're familiar with domain-driven design, you might have seen this pattern. And we've implemented this repository for our old database. We'll call that database A. So we have an A repo that does some database query and it gives you back an account. So to use a repository in our application, we simply call the find method from our service. Our service is probably doing other things besides this, but we're just going to focus on this repository part. So how would we modify this code so that we can connect to both the old and the new database at the same time? So we'll introduce the concept of a mode, which tells us if we should write to database A, database B, or to both. And this mode is going to be driven by our feature flag. So somewhere else not shown here, we're using flags to sort of decide. So we have sort of a 3-mode flag, if you will. And then based on the mode that we're in, we have some kind of messy if-else branching in the code. If we're in mode A, or if we're using both databases, then we'll use repo A. If we're in mode B or using both, we'll use B. And if we're using A and B, we'll compare the results, as I mentioned, so that we can verify we get the same answers. And we'll somehow save the result of that comparison. So this isn't too bad. There are some problems. We don't want to sequentially call repo A and repo B, because that is going to make performance for our users worse and expose them to slowness in the new database, which is database B here. We also haven't put any metrics in. We want to measure and be able to compare apples to apples in terms of the old and the new repositories. So we want metrics around these find methods. So we can try to add these things. As you can see, this code is starting to get complicated, but we've added a couple of Go routines here to hopefully get some concurrency and improve latency. We've added some tracing or telemetry around each repo call. I'm not going to go through this, but the point of it is that you can see if you had to do this in lots of call sites in your application, the chance of you like introducing bugs or doing something wrong is pretty high. This is pretty error-prone code, and it's a bit of a hassle. However, if we did do this in lots of places, we'd probably see that this is pretty boilerplate code. It's essentially doing the same thing in all the different call sites. We would apply this pattern. I'll also add that even with this complex code, there's still some problems. The latency here would be the worst of A and B, which isn't great if the new database B is taking 10 seconds for some reason. We don't want to expose our user to that. And as I mentioned, the code is hard to follow. So it still needs some work. So what we'd like to do is think about how can we get back to this in our application code where it's just a simple call to a find method, and somehow make that talk to both databases. So we can do that by factoring out the cross-cutting concerns like the instrumentation, the feature flagging to select the mode, how the 2 database calls are executed relative to each other, how the concurrency works, and how we're going to verify the results and save the verification or the comparison somewhere so we can look at it later. So because we're using Golang, the idea of build time code generation is pretty well supported. So that's how we solve this problem. This is another area where your mileage may vary. Other languages, you might do some dynamic runtime code generation or proxies. But we solve this by generating some wrappers around each repository interface and adding our metrics to those wrappers, and as well as our feature flagging and our verification strategies. So the way that works is that we add a go generate, which is a standard Golang directive, to generate some wrappers based on this repository interface. And then the tooling spits that out. And then in our application, we set up these wrappers using the A and B repository implementations that have our database queries. So we wrap both of those inside of a sort of switching wrapper. Here it's called a migrating account repository. And that wrapper also has a handle on the thing that provides us which mode we're in, which is backed by flags, as well as how to execute the A and the B calls as a strategy object called a dual executor here. And then we also provided a verifier. So we can sort of plug in our own techniques that we want to do depending on the repository we're migrating. But there's a standard library that provides those implementations, so we don't have to put that stuff in our mainline like request processing code. And because we're using code generation, we also can take the opportunity to associate each method call with a type that captures the package and the Golang type and the Golang method for each of those repository methods. And this is nice because we can use that to target the migration at the method level if we want. So we can use a feature flag to say, I just want to migrate methods that start with the word get, for example, or I just want to migrate methods in this package or that belong to this repository type. It also gives us a way to see metrics on a per method level via the code generation. And as I mentioned, we control the mode, whether we're in A or B or both mode using a feature flag. So this is an example screenshot from the LaunchDarkly application of how you might do that. So we're saying here that if our repository type is an account repository and the user who's making the call to our API, say, is in our guinea pig set of users, then we're going to give them both databases. Otherwise, everybody else, we're going to give just the old database. So this gives us a way to gradually, instead of going dual mode immediately across all of our requests, we can sort of phase that in just so that we get that gradual introduction of the new infrastructure. Even though we've tried to isolate it as best we can, something could still be wrong that we want to not expose everybody to. So there's other ways to do this. If you do synthetic testing, you could target here instead based on your synthetic testing requests, or you could do some sort of percentage rollout. I just want to do this for 1% of my traffic. There's lots of different ways that feature flags give you to sort of control when to make a choice. And so just to summarize, by making some investments in tooling upfront to be able to support this concept of a migration between two interfaces, that could really be any interface. In this case, we're doing interfaces on top of databases. So by doing that, we made it very simple for the application developers who are writing services that use those databases to not have to modify their code, their basically like API request processing code directly. They can rely on the tooling to make sure things are done correctly in a way that's not error prone. We applied flags for peace of mind, being able to have the flags to control what the behavior of your application immediately, plus metrics to see what it's doing, plus verification to see that you're getting the same results from A or B, really makes this whole process, removes a lot of fear from the process and lets you make these changes with confidence. So we were able to do migrations in production, essentially testing them in production. We found problems, of course we made some mistakes and we fixed them as we iterated, but the main point is that no customers noticed that we were doing this. And we were able to sort of shield them from the work that we were doing. And that brings us to the end of my talk. Thank you all for listening.